Zero-knowledge protocols allow a prover to prove an assertion to a verifier, but without revealing anything. And in this video, you're going to learn what these protocols are, you're going to see an example, and you're going to see how they're used in cryptocurrencies. Hi, my name is Lior Malka, and you're watching the channel on Next Generation Cybersecurity. Today we'll be talking about zero-knowledge protocols. When I did my PhD back in 2008, zero-knowledge protocols were pretty much an academic concept, so they weren't really used much in industry. But things have changed, and today zero-knowledge protocols are used in several places, and we'll talk about how these protocols are used in cryptocurrencies, and especially we're going to be talking about zCash. This presentation about zero-knowledge protocols is going to be deeper than most videos out there, and if you feel that it's too heavy, feel free to skip to the end. In the first part, we'll see a motivation to zero-knowledge protocols. In the second part, we'll talk about zero-knowledge proof for quadratic residuosity, and if you feel that this part is a little too heavy, feel free to skip to the third part. In the third part, we'll see what is Bitcoin, just briefly, and then we'll see what is zCash again, very briefly, and we'll talk about how zero-knowledge protocols are used in zCash. Now, this presentation is not about zCash, and we're actually not going to see the zero-knowledge proof that is used in zCash. So the idea is just to give you an understanding of what zero-knowledge protocols are and where you can use them, and give you enough tools that you can actually go and read academic papers. So this presentation is pretty deep, and I hope that you'll enjoy it. So to motivate the idea of zero-knowledge protocols, let's look at a very intuitive scenario where you have a user and they want to log into their bank, and they want to prove to the bank that they are the legitimate user. So one way to do it, which is the simplest, is to have the bank have a database with usernames and passwords, and have the user send their username with the password over a secure channel, of course, and then let the bank compare the password sent by the user to that stored in the database. This is a very simple and naive approach. The reason why it's naive is because anybody who breaks into the bank or employees of the bank can see the passwords of the users, and that's not a good thing. So the next obvious improvement would be to hash the passwords. Now, a hash, for those of you who don't know, is a function that is essentially one way, meaning you can compute the hash easily, but to invert it is going to be difficult. It doesn't mean that there are no attacks on hash functions. It just means that it's difficult for attackers to invert the output of the hash, which is actually called the digest. So in the scenario where the bank hashes the passwords, the user is still sending their password to the bank, because the bank needs to compute the hash over the password that they receive from the user and then compare it to what they have in their database. This is not a zero-knowledge proof, because the user is actually proving that they are the legitimate user by revealing information that the bank does not have. The information that the bank does not have is the password of the user. The bank only has the hash of the password, and computing the password from the hash is not something that the bank can do efficiently. And for those of you who don't know, when I say efficiently, I mean in polynomial time. Now, the reason why we may want to improve a system where banks store the hash of the passwords is because in this slide it looks like it's not a real issue. The password comes on a secure channel and being compared immediately with the stored value. But in reality, there are many systems through which the password is flowing. It can flow through a firewall, it can flow through a VPN, it can flow through many things, and it creates a digital trail, and anybody on this trail can see the password. So this is still not a good solution. The next improvement over hashes is to use public key cryptography. The idea here is that Alice is going to create a key pair made of a public key and a secret key. The public key is public and the secret key is secret. She's going to use the secret key to sign messages, and in doing so she's proving that she owns the public key. Let's see how it works. Alice first sends her username to the bank. The bank has an association of their username with her public key. So the bank is going to choose a random number and send it to Alice. Alice is going to sign this random number and send it back to the bank. The bank will take the public key and use a verification function to check that the signature on this random message is indeed done by the owner who has a secret key. So this is essentially a proof that Alice owns or knows the secret key. But this is not a zero-knowledge proof, and here is why. When Alice sends a signature over a random message, she's actually giving the bank information that the bank could not have produced on its own. Think about it. If the bank has your public key, can it produce a signature over a random message? No. Only the owner of the secret key can produce a signature. Now you may think that having Alice sign a random message is not a big deal, but actually think about it. What if somehow, instead of sending a random string, somehow someone could have Alice receive a cryptocurrency transaction, like a Bitcoin transaction, and Alice would somehow think that this is just a random message from the bank, so she's going to sign it, but this is actually a transaction to transfer money, Bitcoins, from Alice to somebody else. So now Alice has been tricked to sign a transaction for moving Bitcoins from her account to somebody else. Now, of course, I'm not saying that this attack is actually possible or that it cannot be mitigated. It can be, but I'm just trying to give you an idea that when information is leaked in a protocol, there could be unforeseen consequences. So now let's see how it's going to work with zero-knowledge protocols. The zero-knowledge solution to this problem is actually similar to the public key, secret key solution that we've just seen. However, it does have a big difference, which is it leaks no information whatsoever. The idea is basically that Alice is going to pick two numbers, x and y. X is the secret and y is a number. X is actually going to be the square root of y, but not exactly. We'll see soon why not exactly. Alice is going to send a message to the bank. The bank will send a challenge and Alice will respond to the challenge. So there will be three messages, A, B, and C. And at the end, the bank will verify the messages that Alice has sent and will conclude that Alice either knows the secret X or that she does not know the secret X. And through this proof, no information will be revealed to the bank at all. The only thing that the bank will learn is that Alice indeed knows X. Now, the advantage of this protocol over the public key protocol is that in the public key protocol, Alice was leaking some knowledge to the bank, and if someone was listening on the communication channel, they could use this information to their benefit. However, in this case, Alice is using a zero-knowledge protocol, so it doesn't matter if someone hacked the bank or if someone hacked the communication channel between Alice and the bank, they cannot use any of the information that they see to compromise Alice's security. Now we're in the second part of this video and we're going to talk about the zero-knowledge proof for quadratic residuosity. Now, like I said in the beginning, this zero-knowledge proof is not the proof that is used in zCash, but the reason that I'm giving you this proof here is because it's simple and we'll be able to cover it from A to Z. So you'll be able to see all the qualities of a zero-knowledge proof and you'll get a complete understanding of how zero-knowledge proofs work. Like I said, there is a lot of math in this part, so if you don't like it, just skip to the next part. The first thing that we will need to talk about is integers. And especially we're going to be talking about multiplication, square root, and square. In the integers, we have all the numbers from 1 to infinity, and we mark the set with curly brackets. Now, multiplication in this set is pretty simple. For instance, 1 times 2 is 2, 5 squared is 25, and the square root of 9 is 3. Now, in the zero-knowledge proof, we will not be using the integers, we'll be using the multiplicative group of integers. So in the multiplicative group of integers, there is only a subset of the integers. For instance, in Z7, there would be all the numbers from 1 to 6. The reason that I've chosen Z7 is because Z7 has all the numbers from 1 to 6. So it's easy to show an example with Z7. But in the zero-knowledge proof for quadratic residuosity, we'll be using Zn where n is not a prime. And in this case, Zn does not contain all the numbers from 1 to n minus 1. It contains just a subset, but it doesn't make any difference in terms of the multiplication operations. So in Z7, we have the numbers from 1 to 6, and we do multiplication using the modulo operation. So for example, 1 times 2 is 2, and 2 is in the set, so there is no need to do any modulus. But if we do 5 squared, the result is 25, which is outside of the set of numbers from 1 to 6. So what we do then is we divide by 7 and we keep the remainder. The remainder is 4. Therefore 25 modulo 7 is 4. Now the square root of 4 modulo 7 is 5. The reason we know it's 5 is because we just saw that 5 squared is 4 modulo 7. But if we didn't know that, it would be less intuitive. For example, take 2. What is the square root of 2 modulo 7? That's not so intuitive, right? You can take all the numbers from 1 to 6 and just raise them to the power of 2 and see when you get 2. So if you do that, you'll see that 3 squared equals 9, and modulo 7, 9 is 2. That means that the square root of 2 is 3. So to summarize, we've seen the integers and we've seen a subset of the integers called Zn, the multiplicative group, modulo n. We saw that in the multiplicative group, computing the square root is not so intuitive. What's really interesting is that computing the square root modulo n is actually known to be a hard problem. This problem is called quadratic residuosity. The quadratic residuosity problem is to find the square root of a modulo n. Now the examples that we've seen before help us understand intuitively that computing the square of a number, even if it's in modulo n, is actually easy, but computing the square root is less intuitive and difficult. So it turns out that for certain choices of n, in particular where n is the product of two prime numbers, so if you take two prime numbers and you multiply them and you get n, if you choose an a from Zn and a has a square root modulo n, it's actually going to be hard to find that square root. Before we move on to the zero knowledge protocol for quadratic residuosity, I just want to mention that the fact that n has to be the product of two prime numbers, that doesn't really matter for the zero knowledge proof. It only matters when you use the zero knowledge proof as an identification scheme. Alice has to choose n, which is the product of two prime numbers, so that if anyone sees y, they can find the square root of y modulo n. So in the zero knowledge proof, we have two parties. We have the prover and we have the verifier. In the case that there is a square root modulo n, we'll call this square root x. So the prover is going to convince the verifier that y has a square root modulo n. This zero knowledge protocol is actually very simple. The prover is going to start by picking a random number r from Zn star, and then he's going to raise this r to the power of 2, basically compute the square of r. The prover is then sending this first message, which we're going to call A, to the verifier. The verifier is going to pick a random bit and send it to the prover. The prover is going to send the third message C to the verifier based on the bit B. So if the verifier sends 0, the prover will answer in one way, and if the verifier sends 1, the prover will answer in a different way. Eventually, the verifier gets the message C and decides whether to accept or reject the claim of the prover that y has a square root modulo n. Let's see the details of the proof. So when the verifier sends the challenge bit b equals 0, the prover simply responds with a randomness that the prover chose in the first step. So the verifier in this case simply checks that the prover sent the first message A as he was supposed to do. When the verifier sends the message 1, he expects the prover to send the message XR. Basically, the idea is that XR raised to the power of 2 should also be a square root of some number, and that number is A times Y. The reason for this is that A equals R squared and Y equals X squared. So A times Y should have a square root modulo n. So to summarize, when the challenge bit B equals 0, the prover simply reveals the randomness. And when the challenge bit B equals 1, the prover reveals X times R. And notice that X times R is a randomized version of the secret X. The prover does not reveal X, he randomizes X. So in both cases, the prover does not reveal anything to the verifier, but we will see that formally in just a bit. For now, let's check the properties of this protocol. A zero knowledge proof needs to have three properties. First of all, it needs to have the completeness property. Completeness means that if y has a square root modulo n, then the verifier accepts. The second property is soundness. It means that if y does not have a square root modulo n, then the prover cannot convince the verifier. And the final property is the zero knowledge property. This property means that the prover leaks no information to the verifier. And we're actually going to formalize this notion in just a bit. Before we move on, notice that in the protocol that I just showed you, the verifier always accepts if y has a square root modulo x, which means that the completeness property always holds. One more thing to notice is that the zero knowledge property actually does not require completeness and soundness to hold with probability 1. Even if completeness holds with probability 2/3 and soundness holds with probability 1/2 or 1/3, even that is fine. And actually you will see that the soundness property holds with probability 1/2. Let's examine the soundness property now. Let's say that the verifier accepts with probability more than 1/2. If the verifier accepts when b equals 0, it means that the verifier accepts when a equals r squared. But if the verifier also accepts when b equals 1, it means that a times y equals c squared, where c is the third message of the prover. So what does this tell us? We can substitute a with r squared and get that r squared times y equals c squared. Then that means that c divided by y when squared equals y. And this means that y has a square root modulo n, which is impossible because we just said that y does not have a square root modulo n. We said that the prover is trying to cheat the verifier. So what we're getting here is that the prover cannot cheat the verifier with probability more than 1/2. Okay, so let's remember, we're talking about a zero knowledge proof. We saw that the completeness property is holding and that the soundness property is holding with probability 1/2. The last thing we need to do is to show the zero knowledge property. Now we're going to actually show how the zero knowledge property holds, and we're going to do it formally. So let's think about probability spaces a little bit, okay? When the prover talks to the verifier, there is an exchange of messages. And this exchange of messages, of course, is different from one interaction to the next. The interaction has the messages A, B, and C. All these interactions actually create a probability space where each interaction has a certain probability to occur. Now, the reason why we care about this probability space is because whatever the verifier learns from the prover, the verifier learns from the interaction, from the messages A, B, C. If we can somehow show that the verifier can generate those transcripts on his own without interacting with the prover, then we actually show that the proof leaks no information because the verifier can generate those messages on his own. So for that, we need to show a simulator. The simulator is basically going to generate transcripts, meaning messages A, B, and C. And the simulator needs to create those messages with the same probability that those messages appear in a real interaction between the prover and the verifier. Now keep in mind, the verifier is a polynomial time Turing machine, or essentially it's an efficient computer. So in order to show the zero knowledge property, it's important that the simulator also runs in polynomial time. The idea behind the simulator is that the simulator actually doesn't know the secret, right? The simulator is essentially an extension of the verifier. So if the simulator doesn't know the secret x, he only sees the common input, which is y and n. How can the simulator really generate a transcript? The trick here is that the simulator is going to work in reverse. It's basically going to guess what the verifier is going to ask, and then it's going to prepare the messages anticipating that the verifier will send that challenge. And if the verifier sends a challenge that's different from what the simulator has anticipated, then the simulator can simply fail and not output anything. Which is okay because the verifier can simply run the simulator again until it gets a transcript. The simulator is going to work like this. It's going to first pick the last message C, and it's going to compute C as R. So simply it's going to pick a random string from Zn, and that's going to be the last message C that the simulator will produce. Next, the simulator is going to pick a random bit B, either 0 or 1. If B equals 0, the simulator will set the first message A to be R squared. But if B equals 1, the simulator will set the first message A to be R squared divided by Y. Despite the fact that the simulator computes its messages in reverse, it still guesses what the verifier is going to ask. So the simulator is going to work like this. It's going to compute all the three messages A, B, and C. Then it's going to send the first message A to the verifier. And if the verifier replies with the same B that the simulator anticipated, then the simulator will send C to the verifier. So now we're at the heart of the zero-knowledge proof. We want to show that the output of the simulator creates a probability space, and we want to show that this probability space is identically distributed to the probability space that is generated when the verifier interacts with the prover. So there are two probability spaces, and we need to show that they are identically distributed. So the first thing to notice is that in transcripts of the form r squared 0r, meaning the verifier sends the challenge bit b equals 0, the distribution is identical to the distribution in the real proof between the prover and the verifier. In the case where the simulator sends r squared divided by y to the verifier, that's different from what the prover would have sent. The prover always sends r squared, but there's no difference really between r squared and r squared divided by y. And if you want some intuition for this, think about the following. Imagine that you have a fixed string and you XOR it with a random string. The result is going to be a random string, right? So whether you take a random string or whether you take a random string and you XOR it with a fixed string, you'll always get a uniformly distributed random string, right? So the same thing here, r squared divided by y is distributed identically to r squared. That's why even though the simulator sends r squared divided by y, it's distributed exactly like r squared. What this tells us is that not only the first message, namely r squared divided by y, is identically distributed to the first message in the interaction between the prover and the verifier, but also the second and the third message are identically distributed. This concludes the zero-knowledge proof. We actually showed three properties here: completeness, soundness, and the zero-knowledge property that we have demonstrated using the simulator. Let's review what we've seen so far. We've seen the zero-knowledge proof, where the prover can convince the verifier that a number y has a square root modulo n. And we also discussed before that if n is chosen as the product of two prime numbers, then it's going to be hard for anybody seeing y to find the square root of y. So if that were to be used in a logging example that we've seen before, the prover, which in our case is Alice would be able to convince the bank that she knows the square root of y modulo n, but without revealing any information to the bank. And anybody seeing y would not be able, at least not easily, to find the square root of y modulo n. So that recaps zero knowledge for the login example. Now, I don't want to define another notion of zero knowledge, but basically there is a notion of a zero knowledge proof of knowledge, which is when the prover not only convinces the verifier, but he is actually showing the verifier that he knows some certain secret. And in fact, the zero knowledge proof that we've just seen is a zero knowledge proof of knowledge. This is the kind of zero knowledge protocol that's used in zCash. We're not going to see any other zero knowledge protocol or proof in this presentation. However, I'm briefly going to touch on these different notions of zero knowledge so that if you go and read the literature, you're well prepared. So the first notion of zero knowledge that I want to talk about is interactive versus non-interactive proofs. The proof that we saw for quadratic residuosity, that was an interactive proof because it involved messages going both from the prover to the verifier and from the verifier to the prover. Some zero-knowledge protocols are non-interactive. In that model, there is a common reference string, which is typically a random string, and the prover simply sends one message to the verifier. What's attractive about this model is that there's only one message, and this message can be used to convince many verifiers, not just one verifier. Another interesting quality of non-interactive zero-knowledge is that there is a way to make them succinct. In other words, instead of the prover sending a long message and the verifier taking a very long time to verify that message, there is an improvement that allows the prover to send a very short message relatively and for the verifier to verify that message very quickly, relatively. So those improved zero-knowledge protocols are called succinct. And in the zCash protocol, they use a succinct, non-interactive zero-knowledge protocol. Another aspect of zero-knowledge is that some of the protocols are specific to specific problems, while others are more generic. So for example, the protocol that we saw for quadratic residuosity, that was a zero-knowledge protocol for a specific problem. There are other zero-knowledge protocols that are specific. For example, there are protocols where the prover can prove that any number n is the product of two prime numbers. However, there are also generic protocols for proving anything. For example, a prover can prove that a certain value y is the hash of some value x, but without revealing anything other than that. In particular, not revealing the value of x. And those are the kind of things that are used in the zCash protocol. In order to prove those more generic assumptions, the zCash protocol uses a generic zero-knowledge protocol. Now, I'm not going to get into complexity theory, but basically statements like y equals x squared or y equals the hash of x, all of these statements are basically NP statements, and what that means is that they can be reduced to a common statement, and that statement has a zero-knowledge protocol. You can read more about NP completeness and about zero-knowledge proofs for NP complete problems, and this is actually the kind of zero-knowledge protocol that's used in zCash. Now, another notion of zero-knowledge protocols is proof versus arguments. In a zero-knowledge proof, the soundness property, meaning the ability of the prover to cheat the verifier, holds with respect to any prover. So even if the prover has unbounded computational resources, even if he's a quantum computer or he has a cluster of machines and he can use a lot of computational power, the prover cannot cheat the verifier except with some small probability. And in the zero-knowledge protocol that we saw for quadratic residuosity, this was the case. No matter what power the prover had, he was not able to cheat the verifier with probability more than half. Now, in some zero-knowledge protocols, like the ones for generic zero-knowledge problems, the prover actually uses a hash function, for instance, to hide some information, and then he discloses the value that was hidden in the hash function. Now, the soundness property relies on the fact that the prover cannot open the hash function to a different value than what was originally sent to the verifier. So if the prover has unbounded computational resources, then obviously he would be able to open the hash function to a different value, and that's going to break the soundness property. So in this case, the zero-knowledge protocol has a soundness property that assumes that the prover cannot break or invert the hash function. And those kind of zero-knowledge protocols are called arguments. They're not called proofs. They're called arguments because the soundness property relies on the fact that the prover is computationally bounded. Now, another thing about generic zero-knowledge protocols that use hash functions or some other functions to hide information, those functions hide information, but they're not perfectly hiding the information. So in this case, the zero-knowledge property is not perfect. It's called statistical. And what statistical means, it means that a very, very small amount of information is leaked. So to summarize, we have talked about different notions of zero-knowledge protocols. We started with the notion of a succinct, non-interactive protocol, which is a protocol where there is only one message from the prover to the verifier, and it's a short message that can be verified efficiently. So it's a succinct, non-interactive protocol. The next thing that we talked about is arguments. Arguments are not proofs. They are zero-knowledge protocols where the soundness property holds under the assumption that the prover is computationally bounded. And we talked about statistical zero-knowledge, which is zero-knowledge proofs that are not exactly perfectly providing privacy to the prover, but just statistically providing privacy to the prover. And this is the kind of proof that's used in zCash. It's a ZK snark. Now we're moving on to the third part of this presentation. We're going to see how zero-knowledge protocols are used in cryptocurrencies. To motivate this discussion, let's take the example of Alice who wants to transfer some money to Bob through a bank. In this case, we're not talking about cryptocurrencies, we're talking about banking. Alice would first need to log into her bank. That's how the bank is going to verify her identity. And when she's making a transfer, they already know that Alice is Alice, so they don't need to ask her again to prove that she's Alice. She can just make the transfer. And both her identity and the money that she transferred to Bob are kept private because this is a private system. Now in cryptocurrencies, of course, the situation is completely different. There is no database of usernames and passwords, and there is no table of balances. But there are similar things, and the way those things work is that Alice has a public key and a secret key. Same thing with Bob. And they use those keys in two different ways. First of all, when Alice wants to transfer money to Bob, she says, I want to transfer so much money, let's say 5 bitcoins, to Bob. And she signs that message. By signing this message, the Bitcoin system can verify that the message indeed came from Alice. So this covers the identity or the authentication part of the protocol. But now what about the balance? How does the Bitcoin system know that Alice actually has the funds to pay for the transaction? For this, the Bitcoin system has a file that contains all the transactions that have been made. This file, of course, is too big, so it's broken into blocks, and together it's known as a blockchain. When Alice submits her transaction to the Bitcoin system, Alice also specifies to the nodes in the Bitcoin system which past transactions are transactions that delivered funds into Alice's account. So for example, Alice can say, here's a transaction where Carl gave me 2 bitcoins, and here's a transaction where Dave gave me 3 bitcoins. Those are called the inputs for the transaction. Alice uses those inputs to transfer her 5 bitcoins to Bob. Now if you look at this example, you're actually gonna start appreciating the difficulty of taking this Bitcoin system and making it private. Because the public keys, as much as they are just random numbers, they do represent identities, and identities can be traced back to those public keys. In the same way that a phone number may be just a number, but a person can be associated with a phone number, and then that phone number can be used to track the activity of that user. Same thing here. The public key, even though it's just a random number, those public keys can be associated with users and reveal how much money the user has and how much money they've transferred and so on. So how can we make it private? This is what the zCash system is trying to achieve. It's trying to bring the benefits of the Bitcoin system together with stronger privacy guarantees for senders and receivers of Bitcoins. Now, before we go into zCash, I just want to say, and I said it earlier in the beginning, this presentation is not about zCash. I have no association with zCash. I'm not promoting or endorsing zCash. I'm just giving you a high-level overview of zCash, and I'm just trying to help you understand how zero-knowledge protocols are used in zCash. And again, we're not going to see the actual details of the zero-knowledge protocol that's used in zCash. We're just going to see the high-level principles. Because the zCash system is built on top of Bitcoin, it has all the Bitcoin components. So it has the public key and the secret key that each user has, and they use it to make regular transactions, just like in Bitcoin. So for instance, Carl can give Alice 2 bitcoins and Dave can give Alice 3 bitcoins, and Alice can then take those coins and transfer them. Now, in the zCash system, there are 4 kinds of transactions. The first one is the Bitcoin style transaction, which is a transparent address in the zCash terminology. And then Alice can transfer the money to Bob without disclosing the identity of Bob. So those addresses that are hidden are called shielded addresses. The transaction from Alice to Bob is in this case from a transparent address to a shielded address. There are 2 more types of transactions, from a shielded address to a shielded address, and from a shielded address to a transparent address. We will not be talking about all of those. We actually are going to talk just about how money is transferred from Alice to a shielded address, and then from a shielded address to another shielded address. Now, before I go into the description of the zCash protocol, I just want to mention that the details of this protocol are taken from the zCash website. So you can go and follow the same example that I'm giving here on their website. And another thing to notice is that the zCash protocol is actually based on a scientific paper, and this is the paper. It's called zCash decentralized anonymous payments from Bitcoin. So I am not going to follow the paper example. I'm going to follow the zCash example, but I will make references to terminology used in the paper so that if you want to cross-reference the example that I'm giving here with the one that's in the paper, you can do that too. So let's talk about how money goes from public money to private money. And to simplify the example, we're choosing an example where Alice transfers money to herself. The way she does it is she picks a random number, a serial number, and then she concatenates that with her public key. And then she computes the hash of that. So essentially you can think about this minting of the new coin as an encryption of a coin, okay? This value that she gets, the H1, is the hash of the public key concatenated with a serial number, and she posts that to the system. So all the nodes add this value to their tables. Now, of course, anybody can create this value. So in order to do that, Alice has to pay for this coin, and the simplification that we made is that there is a fixed amount of coins. So she's only going to pay 1 Bitcoin in order to create this new minted hidden coin or shielded coin. And this shielded coin is now becoming part of the balance in the system, but nobody knows who owns this shielded coin because it's just a hash. Now that we talked about how Alice creates a new shielded coin, let's see how she's going to transfer this shielded coin to a shielded address. In other words, we're looking at the transaction from a shielded address to a shielded address. Like we said, the spending of the coin involves knowing the serial number. That's why I chose Alice as the recipient of the shielded coin in the first example, because she actually knows SN1 and she can spend that coin. However, now that she's creating a new coin, she's going to create a new coin for Bob. So she's going to take his public key and choose a serial number SN2 for him, for Bob. And she needs to let him know that the serial number is SN2. So she's going to send it to him. Bob will have SN2 and that will allow Bob to spend that coin. Just creating H2 is not enough. Alice also needs to nullify the coin associated with H1. So for that, there is a nullifier set. That's another data structure that the system uses, and this data structure keeps track of all the coins that have been spent. So at this stage, the system has 2 hashes, H1, which is a coin mint of the first coin that Alice created for herself, and H2, which is a coin mint for the second coin that Alice created to transfer 1 Bitcoin to Bob. There is also a nullifier set with a value that nullifies the first coin, the coin associated with H1. But all of these values are just random values. They're hiding stuff. How does the system actually know that Alice is following the protocol, that she's really computing all these hashes and nullifying the correct values? This is where zero knowledge comes in. The first thing that Alice needs to show is that she actually has the funds to move to Bob. So in order to do that, she's going to prove that there is a public key and a serial number such that when hashed, the result is in the set of hashed coins. If you look at the paper, this set of hashed nodes of H1 and H2 is called CM list, coin mint list. The second thing that she needs to show is that she actually knows the secret key SK1 corresponding to PK1. And the third thing that she needs to show is that she actually nullified the correct coin. She's doing that by proving that she knows a value SN1 such that the hash of that value equals NF1. So to summarize, Alice proves 3 things: that the hash node is in the set of hash nodes, and that the content of these hash nodes are associated with her public and secret key, and that she nullified the correct serial number. Now, like I said earlier, all these proofs that Alice is making to the system are zk Stark proofs, meaning there is no interaction, they're non-interactive, they're succinct, they're arguments, and Alice simply posts those proofs to the zCash system, and those statements are actually verified by everybody. Now in the zCash paper, you can see some analysis of the performance of this protocol. For the numbers and the data they have there, the verification process actually takes less than a second, but the proof itself is almost 1 gigabyte, which is a little bit big. If you like to see more content on next generation cybersecurity, don't forget to click on the subscribe and notify button. Thank you very much.